Okay. Sounds like I'm online. Cool. So, hey, I'm Max. This is Stefanie and Matt.
Hi.
It's a little different session than what you saw in the keynote, but I hope it's going to be still very useful for you. I think that's probably one of the only sessions today that will not have AI all over it. I will admit, I actually asked AI to put a picture of me based on what AI knows me, so that's me on the left side. And I tried to dress up like it. Unfortunately, I didn't have the full outfit, but I'll work on it next time. I own a compute infrastructure, pretty deep in the stack. And Stefanie owns VM and VM SKUs that we produce as a products or sell as a products. And Matt is an expert in host networking, and you'll have to interact with them as well. And so I'll skip the abstract because generally the abstract most of you read. We'll talk about CPU architectures. We'll talk about kind of how to get best performance out of your workloads, and also what settings to use. But generally, like when we plan the session for the build, everybody's like, well, it's all about AI and about developers and the app developers, and why do you care about the infra? And so effectively, why are we here? Well, the reason is every couple of days, maybe more often, we get a call from a customer saying, well, I'm trying to scale up, or I'm trying to, do something. I'm seeing DNS resolution failing, or seeing some latency, or I'm seeing some throttling. We look at what they're running. We schedule a call. We explain, and they go like, oh, now I get it. I wish, I would have known it earlier. I will brag maybe a little, like Epic Games is one of the customers that is using our infrastructure or some of the recent stuff we developed. And of course, when I told my kids that I'm having a call with Epic, they're like, oh, you're my hero. But now, of course, the issue is every time there is a latency in the game, they call me as well. Like, is it your fault? I'm like, no, I promise not, but let me look. And so obviously, that doesn't really scale. Like, I love having these conversations. This is how we know what customers are using Azure for. And, the amount of scenarios that we see is amazing. Like, the things, of course, I cannot talk about every customer, but like customers running on Azure today, it's everything. It's, everything you can think about, from ticketing to financials to streaming to gaming to anything. And so we decided to spend a session for this build to just talk about the secret sauce of Azure architecture and why customers are scaling in a different ways, and how do you develop an app that can actually scale, and what CPU, VM SKUs, network settings you can use. And I still promise I'll answer calls when customers call, but I hope to have less of them. And so we'll start with, okay, that was a nice echo. So we'll start with what's going on. And so for the few years or past years, Azure Compute infrastructure has been going through a complete redesign and rewrite and transformation. It's something that you could easily compare to something like changing, plane engines while in the air. Because we have customers running their production workloads, they're powering everything. And meanwhile, we have been completely rewriting the infrastructure underneath them. And that rewrite, we generally call Azure Boost. And so we've been very careful of messaging Azure Boost. It's been in such a keynotes here and there. We kind of bragged about storage IOs. Scott is going to talk about this tomorrow in the keynote. And so we often get asked, like, what is Azure Boost? Like, is it powering my workload? Is it powering, AI? Is it powering SAP? Is AKS supporting Azure Boost? Is it a SmartNIC? It is a storage accelerator? Is it secure? Is it integrated with confidential? The answer to all of that is yes. Basically, this is a component that goes into every node in Azure Fleet, and it runs everything that runs on Azure. Any workloads that you're doing today, any AI agent you've seen in the demos, all of that stuff runs on top of Azure Boost. And that has implications. Basically, what we've tried to do, and pretty successfully so, is build an abstraction layer that allows us to mitigate some of the issues with current customer workloads and make sure they continue running on the right side of this without too many implications. But that has its own limitations. Like the magic is still something that generally, we translate. There is a synthetic path. It goes slower. It has some buffer sizes restrictions, and etc. And so generally, we always tell people, please migrate to new SKUs. Please use the recommended OSs. Please go with the stuff that we want you to use. And once they do it, only then they get the full benefits of their application from latency and performance perspective. Now, I will also mention that we have rewritten every agent in Azure infrastructure to run on the Boost. And most of them are rewritten in Rust. Rust is a language of choice from our perspective, and we'll have more about it in the next part of the demo, or the slides. And Matt actually has a demo on Rust. We'll talk about that. But the thing is, and maybe I'll just use it as a picture of the slides. So here's a Azure Boost card. So this is a magic card that goes into every server that we currently deploy in Azure data centers. Now, you can see a kind of closer look on the picture there. Note the two USB NICs that are basically integrated. This is something that allows us to create an active-active connectivity. And basically, this makes sure that when a port on a switch goes bad, or if we need to update a switch, you actually don't experience any downtime. Of course, this is as you could see, labeled Microsoft, highly proprietary, designed for Microsoft, secured for Microsoft card and hardware. So we actually found some of this on eBay. Real story. We managed to get most of them, but generally people who attempt to play with it don't have much success because it's very hardened and it's basically locked down for Microsoft purposes only. So please don't buy on eBay. If you have any questions, ping me. I'll tell you what it does. And so if you look at what we have achieved with Azure Boost so far, you can see that it's across entire Azure infrastructure. We can do a 14 gigabyte per second managed disk throughput. We're doing 800K IOPS and getting closer to 1 million IOPS. We are doing 6.6 million IOPS on the local storage and 36 gigabyte per second on the local storage as well. Our new releases, which we will talk about, can bring us up to 400K CPS or connections per second. And the thing to note is, or the thing I want to highlight is two numbers. One is more than 20%. So we are not retrofitting old hardware with Azure Boost. All new hardware comes with Azure Boost, which means basically as we decommission old hardware and refresh the hardware in data centers, it becomes Azure Boost. And so when Satya was talking about 7 data centers we just opened last month, all of that is with Azure Boost because it's all new hardware. So we get that question often from folks and like, oh, we have one in Belgium, Does it have Azure Boost? Well, if it's new, it's all Azure Boost. But from fleet perspective, we still have a lot of hardware that's going to continue being refreshed over time. And so it's going to take a few years until entire Azure is Azure Boost. But the other thing I'm going to note here is a sub-second networking maintenance. We have a lot of customers who are doing gaming, or like Epic Games, or streaming, or microtransactions on retail marketplaces. And these customers cannot really survive significant amount of servicing and maintenance. It's kind of funny to the sense that they basically going to say, well, I'm running this team meeting. How do you maintain drivers or replace drivers in the middle of it? And so with Azure Boost, we have actually implemented sub-second maintenance. And when we talked to these customers, they didn't believe us. So we took their production workloads and we demonstrated. The worst impact we've seen is in the game, the bullet was slightly changing trajectory. But everything else looks like complete magic. And so this gives us ability to continue innovating on the Azure infrastructure without any customer impact. And we found it a game changer for a bunch of these customers where basically, many customers picked Azure as their infrastructure because of that sub-second feature. Now, we'll not talk today about how we've done it, but if you're interested in this type of cool stuff, read about PMEM and Linux drivers and user mode. So that's kind of would be my advice. But this is cloud magic at its best. Now, fortunately for me, we don't sell Azure Boost. It comes exactly, we just pay for it when we manufacture. What happens is we expose the Azure Boost capabilities through VM SKUs. And this is a product that basically the customers see. And I'll let Stefanie take over for this one.
Thank you. Thanks, Max. All right. OK. So just quickly, just showing the high-level portfolio view. So over the last several months, Azure's announced several new VM series in nearly all of the VM categories. So these VMs are delivering improved performance and better price performance for a variety of workloads. They also have the enhanced security and reliability from Azure Boost. And whether you're running enterprise or cloud-native workloads, HPC, or new AI workloads, Azure has a portfolio that will meet your needs. So our recent announcements, starting last fall through early this year, we announced the general availability of our general purpose and memory optimized VMs. These are based on 3 different CPUs, Azure's 𝗦𝗲𝘀𝗀𝗀𝗀𝗀 processor, AMD's 4th generation EPYC processor, and Intel's 5th generation Xeon processor. And these CPUs are in our newest VMs and deliver significant performance improvements in compute, memory, storage, and networking. These VMs also deliver at least 10% price performance improvement from their prior versions. We also introduced a new AMD FA series, which has symmetric multi-threading disabled for workloads that are sensitive to the single-threaded performance. And the FA series is available with 3 memory to core ratios with 2, 4, and 8 gigabytes per vCPU, and are available with remote storage only. And in our DL, D, and E families, we offer versions with or without local SSD. And all of the new VMs are available in several regions, and we're continuing to expand those regions throughout the year. So next, I want to talk about the performance considerations for these new v6 VMs. So choosing among the many VM series that Azure offers and architecture types can be daunting, and there's several factors that should be considered, including the performance requirements, your budget, sizing requirements, and regional and zonal requirements. So for the performance and budget aspects, I'll talk about those mainly on this slide. I've tried to give some high-level guidance, but really the best thing to do is to actually test your workload because there are a lot of variables for every workload, and so doing the actual testing plus a total cost analysis will give you more accurate information. So as I mentioned, each of these VMs comes in a range of memory to core ratios and sizes, so you can size your VM as needed for your workload. And some of these VMs have local SSD if you need faster access to your data. Otherwise, they all have access to the managed disks, and those have a range of performance and cost options as well. So if you're looking for the best integer performance per vCPU per dollar, then I would recommend checking out the new Cobalt 100 base VMs based on the ARM architecture. With these VMs, a vCPU is a single-threaded core with dedicated caches. And we've observed relatively linear scaling with the ARM CPU. And so as the system load increases, you should see that performance gradually increase as well. And many modern workloads will run well as is on the ARM architecture without requiring recompilation. The Linux operating system and any workloads written for Linux will work very well on Cobalt. If your workload is compiled for x86, then you have two choices to choose from, both Intel and AMD. So when you look at the AMD offering, those offer the best integer performance per dollar for the x86 architecture. And so if you're looking for the highest integer performance, the FASV6 series would be a great place to start. We've also found that the VMs running on the AMD architecture with 16 vCPU and with SMT enabled, and 8 vCPU with SMT disabled, runs well, especially due to the chiplet architecture, which has the cache on the chiplet. And then if you're looking to get the optimal performance on the AMD architecture, you could choose to compile with the AOCC compiler. And then finally, on the right with the Intel offerings, we have a number of benefits that we see for various workloads. We offer up to 192 vCPUs, which is the largest total number of vCPUs for the V6 offerings, and up to 1.8 terabytes of memory. So data-intensive and database workloads will see performance improvements, also due to the large level cache. The Intel processors will also offer the wide vector units and support the advanced matrix extensions, which accelerates AI workloads. So finally, all of our VMs are backed by Azure Boost. The Intel VMs have the latest Azure Boost technology, so you could get the enhanced performance that Max has touched on previously, and we'll be explaining more shortly.
I think Satya was trying to sell the Cobalt. Well,
yeah.
But yeah, we have a lot of customers, Databricks, Snowflake, that are really using it, yep. And they have really good feedback from how it scales for them.
Mm-hmm. Yep. All right. So as Max touched on too, operating systems are important in order to get the maximum benefit from the underlying infrastructure. And often some of the calls that he gets can be solved by using a more modern operating system. So if your OS you're using is nearing end of life or at end of life, it's strongly recommended that you consider upgrading. You should look for your OS supporting Gen 2 VM images, the NVMe disks, the MANA Microsoft Azure Network Adapter driver, and accelerated networking. So all those capabilities are in the modern VM or modern operating systems. And so we definitely recommend that you check out the list here as well as on our docs pages where there's a fully comprehensive list. And you can find MANA source at the GitHub link there. All right, and finally for capacity and regional considerations, I wanted to highlight the Azure Compute Fleet, which achieved GA just a few weeks ago. We are really excited about this offering and what it unlocks for customers. It enables customers to maximize their ability to acquire capacity. So to make this possible, Compute Fleet allows you to provide a set of VMs or configurations that work for your workload, and then we do the analysis to find the right compute footprint. So you can also optimize for cost by including spot and on-demand VMs in a single deployment. We have some of the largest e-commerce and big data providers using Compute Fleet in production today. So we do have plans on our roadmap and also in preview. Currently, we're attributes-based VM deployments is in preview. And with this, you can specify things like the VM, vCPU, or memory size, or the memory to core ratio that your workload needs. And then Compute Fleet can go identify the VMs that match those requirements. And then we also have, on our roadmap, plans to specify deployment in multiple regions. So if your workload isn't needing to reside in a particular region or isn't dealing with any other latency-sensitive components, you can use this capability and it will deploy you in whichever regions at the lowest cost. All right, now on to just a couple of announcements today. So I'm excited to announce preview of the new network optimized VMs. These come in 3 memory to core ratios, or DL, D, and E families similarly, but when you see the lowercase n, that means it's network optimized. And these VMs are suited for real-time data analytics, high-performance file systems, network virtual appliances, and CPU-based AI and inference workloads. So the main improvements over the standard D, DL, and EV6 VMs are the increased network bandwidth per vCPU, so 3 times more, the ability to configure 4 vNICs at the smaller VM sizes, support for 200 gigabits per second with the 128 vCPU size, and dramatically higher connections per second and up to 2 million concurrent connections. So the preview will be initially with the VMs with the managed disks only, but we'll be adding the VMs with local SSD a bit later in the preview. And we've partnered closely with Palo Alto Networks to ensure their NVA performance is exceptional on this VM. We're excited to bring their NVA solution, leveraging the best Azure technology to customers. All right. And then the second announcement is we have coming very soon a new compute-optimized VM called FXV2. This is powered by the 5th generation Intel Xeon processor. These VMs are ideal for large databases, including SQL, data analytics, some EDA workloads, or any workload that needs high memory and performance than what the ESV6 offers today. So compared to our previous FX series, these VMs support up to 96 vCPU and up to 1.8 terabytes of memory with a 21:1 memory to core ratio. So we're seeing tremendous performance improvements across the board with CPU and the networking and storage. So for any of these VMs, these have the latest Azure Boost as well. And we're seeing tremendous improvement. So if you have any workloads that would fit this type of VM, you can access them at the region shown once they are generally available. So now I'll hand it back to Max to do a deeper dive on the newest Azure Boost networking and storage capabilities.
It's actually
Oh, it's Matt, sorry. Oh, I'm sorry. You can do it.
So, yeah.
There you go.
So now we're going to get to the fun part of the presentation.
Okay, so hi everyone, I'm Matt Reat. I work on the host networking piece of Azure Boost. Max went over some of the highlights here, so I won't drain this too much, but we've done a lot of innovation in Azure Boost to bring up to 200 gig throughput, much reduced servicing times for our networking infrastructure pieces. So things like that your game doesn't lag when we're conducting maintenance across the fleet. Dual TOR connectivity is another big piece of feedback that we've implemented in all of the Azure Boost supported VM sizes. So if you lose a physical switch or one of the cables between the server and the switch, you'll still have connectivity for your VMs. And in the most part, you won't see any interruption at all if that happens. Stefanie talked about network optimized SKUs and the preview for that. We're really excited about bringing higher connections per second performance to our VMs in Azure with those sizes. We're moving connection setup logic into our hardware and the FPGA as part of Azure Boost, and so that will bring much reduced connection setup latencies, and then also the ability to scale to more connections for networking workloads like network appliances, firewalls, that sort of thing. So you might be asking, if I'm a developer of an application, or if I use Azure, how can I get the most networking performance out of these new Boost VM sizes? Well, the first part is pick an Azure Boost VM. So the things like the networking bandwidth limits are much higher even for the smallest VM sizes on the Boost-enabled VMs. Once you have this VM, your operating system needs to support accelerated networking. So this is essentially two parts. One, configuration in the portal that your VM is accelerated networking enabled, which all the Boost sizes are, and then your operating system having support for the virtual function drivers to support accelerated networking. So that's Mana in the latest sizes, and then some of the NVIDIA ConnectX NICs in the older generations of VMs. When it comes down to benchmarking and testing, there's a couple of things that I like to bring up because they always seem to trip people up on initial testing or evaluation of a VM size. The first thing is ICMP ping. So ICMP ping is a great tool to test connectivity between two resources, but it's not a great indication of what your network latency will be. This is due to how we prioritize traffic on the physical network and then also on the Azure Boost card itself. So much better way to measure latency is using a tool like SOCPerf or Latte, where you can measure network latency for established TCP or UDP flows. Another thing on the latency topic that we see a lot of is folks that deploy VMs across AZs and wonder why the network latency is much more than if they're in the same AZ. Well, this goes down to physical location of the resources. So thinking about that sort of stuff when you're testing or benchmarking your application or just VM network performance in general. Talked a little bit about connections per second already, but delving into the details a bit. So, there's two things to take away here. One is that connections are a resource on the Azure platform for your VM. We manage state for each and every network connection that you establish. You'll also hear people refer to these as flows. The basic accounting here is that one connection is two flows, so an inbound flow and an outbound flow, or vice versa. And so when you're looking or accounting for how many network connections can my resource scale, you want to take that into account. And if you're doing something like forwarding traffic, like on a network virtual appliance, your flow limits are going to be reduced by half because you're proxying that connection. In order to scale higher, things like utilizing the network optimized VMs for increased connection setup performance, but then also scaling out your resources so that you can manage more connections or connection-heavy workloads. That's where we see customers succeed when they choose that strategy. Okay, so this is going even a bit further. So the operating system support for accelerated networking is great, and the operating system vendors choose defaults that try to work for everyone. But in scenarios where you're trying to eke out the most performance, or you're running into maybe issues due to packet losses in the guest, there are some things that you can look at and tweak. So if you're seeing CPU lock contention, bursty traffic, messing with or increasing buffers on the NIC, or in protocol buffers like UDP socket buffers and TCP socket buffers can help you queue packets that might have been dropped otherwise. This is something that we've seen help out a lot of customers, specifically in the UDP scenario. If you're running on very large VMs, so the full-size isolated VM sizes or maybe M series, looking at network processing isolation and making sure that your interrupt affinity is set to be on the same NUMA node as your NIC, that will drastically improve network performance or latency for your workloads. And then on latency, I talked a lot on the previous slide about resource proximity, supporting accelerated networking, that sort of thing. But you could also trade a bit of CPU for faster processing of network packets by enabling settings like busy polling. So that's just some of the examples. Every example on tuning has trade-offs that you'll need to consider, and it's often workload dependent. But don't just assume the defaults always work for you. Okay, enough of that. Now for a demo. So I was looking through LinkedIn about 2 weeks ago, and I saw this. Max posted on it. There were a bunch of nice feedback. I'm so excited, really looking forward to see what you have. But I saw this and said, we need a Rust demo. So what does that entail, and why Rust? So like Max mentioned, Rust is well loved by Microsoft, and many of our Azure Boost agents are written in Rust. In fact, some of the translation layer tools that we use for increasing network and storage performance, if you don't support our drivers, are implemented in Rust. Microsoft's a member of the Rust Foundation. But Rust itself provides some loved improvements. So performance equivalence to C and C++ is really important when you're working at the hardware layer like we are in the Boost stack. Having memory safety and reliability enhances security and improves maintainability. And then having deep concurrency and thread safety tooling helps enable workloads to scale. But, go ahead.
Before you go, so Rust is one of my favorite topics. So I'll tell you that when Mark Rusinovich posted on LinkedIn, C++ is dead, everybody moves to Rust. There was a small revolt within Microsoft because we have a lot of developers who's like, you're taking my toys away. Now, I will tell you that we spend a lot of time training Microsoft developers working with Rust. And the most interesting part was that effectively all of the new hires that we get, it's much easier for them to learn Rust. And once they know Rust and go with Rust, they stay with Rust. It's much harder for us to teach URs, or like basically university recruiting of hires, how to manage memory with C++. And in the restrained environments like Azure Boost, we cannot afford any memory leakage. We don't have much memory. And so this is why, we are really, excited about Rust and keep pushing Rust in our internal tooling and the way we execute. So there is a reason for Rust.
Of course. All that said is the team that we tasked with coming up with this demo, and we were going to showcase, connection setup performance, or CPS, benchmarking on our network optimized sizes. The test tooling that we had written to do this is not in Rust. It was in C and C++. And we've developed our application for eking out the most connection per setup performance over many years. So there's deep Rust experience within Microsoft, but not on the team tasked for this demo. Plus, we only had 2 weeks. So Max said we wouldn't sell AI, but we needed AI at least here to get started. So what we did was we took a description of our client and server for our CPS test tool that we had. We took the help text from the output of the tool itself, and then we gave some hints to AI about how our application works, some of the features that we needed to support, some of the output we needed in terms of networking statistics, that sort of thing. And we got something that worked, which was great, but it needed a lot of improvement. Here is the improved application running, and basically what we're on the client, and we're going to. Good.
Oh,
You're good.
You were good, but now you're on. Okay, good.
Okay, so anyway, we started the tool, and what we'll see here is we get around 28,000 connections per second on between source and destination VM, with a connection setup latency around half a millisecond. Now, I'll say our tool that we have For testing things like network optimized VMs, we're able to scale that much, much, much higher. But in 2 weeks, we're pretty happy with the result, putting a developer on this. So the point is not necessarily to focus on, hey, we built the tool to test network connection setup in Rust, but also to explain some of the concepts I was talking about earlier around tuning your operating system and tuning your application. So when we started with this and the code that we got from Copilot, we were only at hundreds of connections per second, which was good that we had something functional, but not good enough to show at build. And so things that we looked at for optimizing connection setup performance. So this is implementing a proper socket operations and a proper socket state machine, because we're establishing TCP connections. Reducing block contention by using atomic operations versus mutex protected counters for our statistics. Introducing parallelism to the application. So batching our socket creation, increasing the thread count so we can establish more connections simultaneously. And then affinitizing to the CPUs that we're using to reduce cache misses, reduce context switching costs, that sort of thing. And that's, the screenshot here is Copilot helping us do that core affinitization in Rust itself. On the Linux side, some things that you can do immediately to get more connection setup performance are disabling connection tracking or changing, and also changing ULIMIT rules to increase the number of simultaneous connections that you can manage within the operating system. Playing around with the TCP options, that sort of thing can also help a lot. And so that brought us 100x perf pretty quickly for this test application. In the future, there's more that we can do, but we'll see how this application evolves along with our existing tooling for testing networking perf. All right, now we're going to switch back to Max and storage.
Okay, thank you, Matt. Yeah, thank you for doing Rust demo in 2 weeks. And the team was, not happy when I told them they need to do it. They were like, oh, but we have a tool, and it's in C++. And now I need Rust. So anyway, I have not encountered too many applications that don't need storage. And generally speaking, storage always is kind of make or break, and there's lots of decisions to be made of using local storage or remote storage, what type of storage, and frankly, AI is just storage greedy. Like everything we work with AI models, building AI agents, it all looks really good on the demo. And when you send a couple of connections, but when you need to process the entire enterprise, storage with SharePoint and data, you kind of need to go faster, and then you get throttled, and then things don't work well. And so a lot of our evolution from the infrastructure perspective, both on compute side and storage backend side, is related to AI. It's really stressing, every bottleneck in the architectural design, and we keep evolving this stuff. And so a lot of Azure Boost magic that we introduced recently is also in the storage area. And so we looked mostly in 2 different scenarios of storage, well, kind of 3, but 2 where we invested the most. One is accelerating Azure managed disks, which is all the Premium V1, Premium V2, Ultra disk, ephemeral disks. We'll talk about it a little later. But generally, we offloaded all of these storage clients and storage transactions to the hardware, because that's what allows us to accelerate these things. And we work very closely with the storage backend team, which announced things like Azure Boost DPU in the past, where they are also trying to accelerate this on their side. And I think we bragged, and we're going to continue bragging, that we are industry leading with 800K IOPS on the remote storage. And the general thing is, I think we are pretty good. and we'll talk about one specific improvement there, which is we are offloading encryption. And because we are offloading encryption, it basically creates a situation where customers no longer need to select between I want to be in an encrypted storage scenario or I want to sacrifice performance. Basically, this 800K IOPS is with encryption on. Now, I will give a small disclaimer. Yes, like we call all of the hardware we introduce Azure Boost, but we have multiple generations. This is coming the newest generation of Azure Boost, which is with Intel v6 SKUs that Stefanie talked about. And so it's going to come to the rest of the SKUs as well, but the initial rollout and that capability to offload encryption is going to be with Intel v6 VMs. Now, we also, one of the things we've done, and there is more things in common in the future, but we also try to create storage optimized VMs, where if you are really storage oriented applications, which I don't know how many people here, think about it, but like SQL Server as an example, we created special SKUs for the type of storage heavy workloads, which is storage optimized SKUs. EBS v5 and M-Series v3 is the ones that we currently promote. There will be more incoming soon, but we are not ready to announce yet. So some things need to remain secret for now. Then the other things that happened, we introduced a new local storage. It's something we call Azure Boost SSD. It's a new technology that is also now deployed in every new hardware that we are shipping. It's a very different type of SSD. It's coming and being abstracted as an NVMe controller. And this is what allows us to build SKUs that allow 6.6 million IOPS and 36 gigabytes per second. This basically got us out of the business where in the past we would create special hardware for local storage optimized workloads, like L series is one thing to note. Now, basically everything is running on the same hardware. We fully accelerated this to the point we don't need any special hardware anymore. This is coming soon, almost happened, but really coming soon. Stay tuned for the announcements. And I will actually show a demo of some of the scenarios. But before I do, it's really important to pick the right storage for your application. So if you're running an application or writing an application that needs to use managed disks, pick up between the cached option and non-cached option. In the Premium V1, we support caching, which means if you have lots of similar queries and mostly read operations, you're going to be better off having Premium V1 with cache, because most of your requests will not even leave the node. They will just get resolved in the local cache. If you're looking at the application which are very latency and price performance oriented, there is lots of writes, it's not a lot of caching, then Premium V2 is your friend. It's effectively the cheaper version of UltraDisk. UltraDisk is an offering we created for like really high scale customers who are also willing to pay a lot. And so Premium V2 is your sort of middle option between UltraDisk and Premium V1. And then use ephemeral disk. So the ephemeral disk is a technology that we integrate into every workload, including AKS, including many of our own workloads running, which is leveraging your local SSD or local storage, but makes it completely abstract. Like you feel like you're operating with remote disk, but effectively using local disk in the process. And so that's kind of very important. Also try to, when you pick up, and especially when you're using disks, pick up the right number of disks. Pay attention to the throttling that you're going to have there, because you're going to be throttled per disk. And in some cases, we're going to support bursting. In some cases, we're not going to support bursting. For example, in the Azure Boost SSD, we are a little less nice about bursting right now, which is something we're actually working on. So we're going to throttle you as you reach the limit, and then we get customers who come and say, oh, I've been doing all this stuff, but it sounds like I'm slowed down. And yes, you will be slowed down intentionally. So pick up the VM SKU size that allows the thresholds that you need. Now, I will finish with a couple of demos just to show that I'm not kidding.
In this demo, we created a Ubuntu VM. It has 12 Azure Boost SSDs attached to achieve better quality of service. On the right-hand side is the host node where this VM is created. We will run typeperf command on the host to monitor CPU usage on the host. Now that the host CPU monitoring is started, let's use the FIO tool to measure performance inside the VM. The workload runs for 2 minutes, and it can reach 6.6 million I/O per second. And while the random read test is running inside the VM, we can see that the CPU usage isn't affected by the workload and is maintained at around 5%. Now, let's fast forward to when the workload finishes after 2 minutes. And here's the output. Thanks for watching.
So this is pretty cool. It basically, as you could see, the application was making a ton of write requests. By the way, 4K buffer size for write requests is what we normally recommend. So if this is configurable in your app, use 4K buffer size. And there was no CPU consumed. But this is exactly the type of scenario where if you're writing something like AI agent, you really want to go this way because, this frees up CPU for all the, data modeling and basically LLM processing. You're not CPU bound through storage access. As I said, this technology is in all of the V6 SKUs that we shipped. So you will see this Azure Boost integrated in each one of them. And there will be a new optimized VMs coming soon that is going to make the things even cooler. And then the other thing, we actually had a very long conversation with lots of our security guys if we should do it by default now across the entirety of Azure Fleet. But generally speaking, this storage encryption or encryption at host is something that, lots of customers ask for, especially financial, especially, folks that deal with some secrets. And finally, AI as well, because all of the models are confidential, they process confidential data, they don't want to share the data with other customers processing the models. And so I would say Azure Fleet as a whole is trending towards we're going to be host encryption encrypted by default at some point of time. But that's been one of the pain points because, well, you encrypt the data, you spend a lot of time on encrypting, decrypting, it takes CPU cycles, it created jitter for many workloads. And so we spend a lot of time by using Azure Boost technology to basically offload encryption to the hardware and get to the point where it's 0 cycles from CPU perspective. All of this stuff is just magic. That allowed us to create demos like this one. And I'm going to narrate it myself because it has no voiceover. But we had the virtual machine configured with 24 more disks using premium storage V1. And we use a 4K write buffer to measure IOPS. There is a tool we call IO meter. And so as you could see, this is 815K. We officially said 800K because we want to be humble. I can tell you the team in internal testing got to 950. But from VM capabilities perspective, we're going to start exposing it soon for some of the storage optimized stuff as well. That's the magic of offloading, but I'll just recap again with we make all these things possible, but they don't work if you decide to continue using V2, V3 VM that is hitting the translation layer. Or if you decided that you're really fun, or working on CentOS or FreeBSD, which nobody else is using, or you really want to use some very customized Ubuntu image that only you know how to update kernel. Or like, and that's a good point, like, Matt talked about the buffer sizes as an example. So once you write an app and it's on your computer and it has no virtualization layer, you have full access to the NIC. And so you just send things over and, things look good. Now, what happens is when you actually have your stuff offloaded using SRV interfaces, effectively the buffer size matters, because if you dump the data into buffer, like in the UDP buffer faster than we consume from it, you're going to get throttled on your own image. And that's what we see with a lot of customers. And this is effectively why we are having this presentation. Please realize there is some magic happening under you. And yes, it's sometimes you would say, oh, most developers don't need to know it. Same as saying, well, you're writing an app, you don't care about basically threads or processes or how the kernel drivers work. You do, because this is what takes you up and makes it great versus, yeah, it just works. And so that's the reason for this session, and hopefully it helps you at least a little. And I think that's thank you. And if you have any questions, now is time to ask them.
How are the kind of new VMs, like the V6s, used in the managed services, like managed database or container apps or app service?
Yeah, it basically, most of the stuff just like app services or container services, if you use them as is, they run directly. By the way, I'm supposed to put please give us rankings or suggestions for improvements. We would really appreciate it. So most of the stuff is abstracted to you because we just work with AKS team, for example, and they start running on V6s, and that becomes, pretty, the things you don't really see. As an example, I can tell you that SQL Azure was one of the first things that ran on Azure Boost a few years ago and moved the entire thing to the Azure Boost. Having said that, in some of these cases, especially with AKS, you get to pick and choose which image you use and what VM sizes you want to use as well. And so, it's important for you to configure your app to say, oh, run my container service using V6s or use one of these images that we recommend. Don't just trust it's going to happen by default, because the default is going to go into previous generations many times.
I was wondering how Boost SSD works, because it sounds like if you're doing NVMe and stuff, you can only get more in the way between the CPU and the disk. So how do you keep that fast?
You're talking about the Boost SSD?
Yes.
Well, it's basically NVMe over wire kind of interface that allows you to have processing of the SSD or access of the host of the VM image. So basically, your VM image, because it's abstracted and effectively you don't really spend CPU cycles on the VM. The VM sends an NVMe request, and the NVMe request is being handled by controller outside of your VM boundaries. So the CPU that is allocated to your VM, you're not seeing any hits. This is where it becomes a magic. Awesome. Thank you so much. Enjoy build. Hope you learn a lot. And any feedback you have, please feel free to send us.
Thank you.